All right, everyone. So this is then chapter 14, which is going to be on simple harmonic motion, or basically generally on oscillations. All right. So you can see that the goal of this chapter is to understand system that oscillate with simple harmonic motion. So in this chapter, we are introducing new type of motion, as you can see, right? Simple harmonic motion, and this is sort of like an application of the general category that we call oscillations. So that means there's an oscillatory motion, an object or system that undergoes an oscillatory motion can also undergo a simple harmonic motion. So simple harmonic motion is one of the categories within this broader category of oscillations. All right, so let's look at oscillatory motion first. So we have a lot of examples around us, even sort of like, let's say, in nature, where the system can oscillate over time. So for example, you can see the bird or butterfly, right, of their wings back and forth, back and forth. So that's an example of oscillatory motion. Then you can have, let's say, you drop a ball, goes, hits the ground, comes up, goes, hits the ground, comes up, back and forth, back and forth. That's an oscillatory motion. Earth spinning on its axis, it's also oscillatory motion because it's, spins 24 hours and then basically does it again and again and again. Earth going around the sun, that's also an oscillatory motion, or sometimes known as a periodic motion, because after 1 year it repeats the cycle. Or the moon going around Earth, right? 30 days and repeats, 30 days and repeats. So those are the examples of periodic or oscillatory motion. And that means anything that basically repetitive, right, over some kind of period of time. And the time for one oscillation is known as the period. And we have seen the period already before this. So this period T, so this period T is basically known as the time for one full cycle or one oscillation or one revolution, right? So that means when after that the system repeats the same type of motion. So that's basically the period. And we also know the frequency. So the frequency is the reciprocal of the oscillation. So if the period, if the period is how long does it take for the system to oscillate one time, then the frequency is in 1 second, how many times does it oscillate? So basically it's, oscillations per unit time, where the period is time for the, oscillations, time per oscillations. And these are the equations that relate period and frequency. You can see they're reciprocal. So the period has the units of seconds. The SI unit for the period is seconds. And then the frequency, which is 1 over the period. So basically 1 per second, but we define that to be hertz. Hertz is a second, 1 per second. So that's a unit for the linear frequency. Because remember, we're also going to look at something new, which is angular frequency, which we're going to see that it is related to these two quantities, linear frequency and the period. So the angular frequency basically has units of radians per second, and it's not defined as hertz. So it's radians per second, where linear frequency is per second or just hertz. And also you can see here is that when graphed in terms of position versus time, that means the motion of the system as a function of time. If you do position versus time, you're always going to get a oscillatory graph like that. So periodic, that means in the shape sometimes is always going to repeat itself. So it can be something like this, right? So the oscillation takes place around an equilibrium position, and then or something like that. And again, it's also a periodic, right? Because you start from here, going, come back, going, come back, and so on and so forth. Or it can be very nicely, sinusoidal graph like that. So as oscillation, in a way, you can model it, all of them to be, under some right condition to be sinusoidal, where the period represent the time from one, let's say, cycle to another. So that's basically, you see, right? So going from maximum to another maximum, or from minimum to another minimum, that's, the time it takes, right, is basically one period t. That means in a graph, position versus time, period represents that time for basically one cycle, And regardless, right? Let's say in terms of this, which part of the shape of the graph you choose, when you look at the time when it starts repeating, that time interval is the period. Now, not every oscillatory motion can be considered as a simple harmonic motion. Okay, that's because there's one specific condition must be satisfied for the system in order for the system to be considered simple harmonic motion. Okay, so it's some kind of like specific or particular kind of oscillatory motion. And two best examples of systems that behave like simple harmonic motion, that means they do have a simple harmonic motion, is the spring or the block attached to a spring, so basically the spring system, and the pendulum. So that's why in this chapter we will be concentrating specifically on a simple harmonic motion, and two examples that we're going to look at is the spring system and a pendulum. So we're going to start with, let's say, a simple cases where for example, the spring undergoes simple harmonic motion, which I'll explain again in a minute. What are the conditions? What does it represent? But let's say the system goes back and forth on a frictionless surface. So that's a little bit simpler to go over, a little bit simpler to explain. And at the end of the chapter, we're going to see an example where the system can be moving, on a rough surface. And in that case, like let's say a more complex, scenarios come into play where then the system basically can slow down and stop. So, but in this particular, let's say case, when we start going over the spring system, we can assume it's a, frictionless surface. So the object undergoes oscillatory motion between two, let's say, maximum compression and expansion distances. So we'll talk about that. Also, we're going to start with the pendulum. We're going to start with the simple pendulum, which is just basically small mass attached to a end of a string. And then we're going to look at a physical pendulum, which can be, let's say a ruler, right, going back and forth, or one of those grandfather clocks going back and forth, right? The pendulum, which is basically physical, because then you have to look at moment of inertia, then you have to look at the torque on the system and all of those things. All right, so let's start with a spring system. So, and you can see here is the air track glider attached to a spring. And then the air track is basically important in a way that it creates a frictionless surface. And this is something we also do in experiment in class, right? Whenever we have, let's say, actual experiment in class, we do have our ability to have a air track where the air coming out of the small holes on the track represents basically sort of like a frictionless, as possibly as we can get, as close as we can get to a frictionless surface. And then air track and the cart can glide basically without really losing its energy and things like that. Because remember, friction can dissipate energy, right, and can slow it down. And the frictionless surface will allow us to, let's say, no energy being dissipated due to, let's say, some kind of non-conservative forces. All right, so let's look at then an example where we have a air track, let's say surface, right? And we have an air track and you have a cart attached to a spring. So then you take it, you move it to some, let's say from its equilibrium position, let's say, which is right here, move it to position A. So you move it to here, let's say like this, right? And you let go. Because there is no friction and because there is this restoring force from a spring, which, we talked about before, the system will be then pulled toward equilibrium, but it's moving toward equilibrium, it's being speeding up because there's a force acting on it, all the way toward equilibrium, right? And it's going to be speeding up, reach equilibrium, but not stop, then move to the left of the equilibrium. But as soon as it starts moving left of the equilibrium, right, somewhere over here, then the force, the spring force, going to be acting on it in the opposite direction, because the restoring force always acting in the direction of the equilibrium. So when you go to the left of the equilibrium, then this force basically changes direction and acting, in the direction of the equilibrium. So the system that is moving to the left now has a force acting on it to the right, will then slow down and eventually, let's say, stop at this position. When it stops at that position, then this restoring force will be the strongest. So it's going to pull it to the right again. So it's not going to be moving to the right, speeding up all the way to the equilibrium position, because the force is pulling it all the way to that direction. passing the equilibrium, then force is going to be in opposite direction, then it's going to slow it down, and then the system will then slow down all the way to this A position. That means the system will then go back and forth, oscillate back and forth between this positive A and negative A, which are actually, positions that we call maximum positions. So this position A and negative A, we're going to say that they're known as a maximum displacement or the amplitude, right? So the system will then undergo oscillatory or a periodic motion between those 2 points. And again, if there is no friction, it will always come back to position A, and then on the other side, go to position negative A, come back to A, go to the negative A. And if we plot this motion right on a graph, we're going to see that it's a nice sinusoidal graph like that. So that's why the simple the spring system, as it undergoes displacement between, if when you stretch it, you let go, it's going to undergo oscillatory motion. Okay, so it's going to go back and forth, and then the graph of the position versus time graph is going to be look like a sinusoidal graph like that. Okay, again, when we take this and we move it to this position A, that's going to be, the maximum displacement we're going to have for the system uh, in a positive direction, because let's say to the right of the equilibrium is a positive direction. So you can see, right? So in this case, a lot of times what we can say here is this position is the X maximum position, maximum positive position. So we represent it with the, amplitude A, and we say plus A because A, which is the amplitude, is always a positive quantity. So let's say when I say plus A means plus amplitude quantity. Then when it goes to the other side, when it's compressing the spring, it reaches the same distance, but on the left of the equilibrium. Then I can say that X max on this side is equal to the negative A, negative being then the negative position of that the same distance as the amplitude. In a way, you can think like amplitude represents the distance from the equilibrium on each side. That's why it's always positive quantity. All right, so again, you can see, right, this is a graph that represents simple harmonic motion. And I'm in a minute, I'm going to show you sort of like, let's say, a nice simulation that represents, the spring going back and forth. And you can see, right, if you're plotting this as a function of time, you do get a sinusoidal graph like that. So you can see the figure A here shows position versus time graph. So this is basically represents our amplitude A, because that's where we start from. So you can see, right, amplitude is roughly 0.17 meters. And then this is equivalent to having the system first sitting in equilibrium. So let's say, let me take from the center, right? So this X equals 0. And then you take it and then you basically stretch it to position A. So then where A here is 0.17 meters. So then we let go. That means we're holding the system in that position at X, at T equals 0. So at T equals 0, it's right here. And then once you let go, it's going to be then speeding up toward the equilibrium because there's restoring force acting on it, right? Speeding up toward the equilibrium. And then as soon as it basically reaches equilibrium, it's not going to stop. It's going to continue moving to the left, but then it's going to start slowing down. So for example, then this graph represents that. See, this is the graph going from X equals A to X equals 0, and it's a speeding up to the left. And this is the graph represent for speeding up to the left. Okay, but we have the spring force, and remember, spring force is just a Hooke's law equation, is equals to negative kx. So this equation, spring force equals negative kx, is then changes direction as soon as it passes the equilibrium. Now the force acting in this direction, when the system is, let's say, somewhere over here, passes the equilibrium position. As soon as it does that, it then starts slowing down all the way until x equals negative a position. And this is the graph for the slowing down going to the left. So this is a graph for slowing down, and it stops exactly at negative 0.17 meters. Then the force is going to make it speed up all the way to equilibrium. So this is the graph speeding up toward the right. As soon as the system passes equilibrium again on its way to the positive A, then it's going to slow down until it stops at A. And then again, after that, it repeats. So speed up all the way from A to 0, then from 0 to negative A, it slows down, then speeds up from negative A to 0, then slows down from 0 to to positive A, and it repeats the cycle. That means it goes back and forth between those positions, where if you do the slope, remember the position versus time graph, the slope of the graph is the velocity. If you do the slope for positive a and negative a, you can see that slope is zero, means that this means that speed is zero at, here you can see, right, velocity or the speed is zero at x equals plus minus a. And then you can see, right, if I'm looking at the speed at x equals zero, or the slope, I get the steepest one at x equals zero. That means the speed is the maximum at x equals zero. That means when you take the spring and you stretch it to position A and you let go, it starts from rest. So that's why there is no velocity over there. And then it starts speeding up all the way to x equals zero. So that means that x equals zero, it's moving the fastest. And then after that, it starts slowing down because force changes direction. So it starts slowing down. And as soon as it starts slowing down, basically it reaches x equals minus a and it stops. That means at x equals minus a, again, it has no velocity. All right, so taking this velocity position versus time graph, we learned that, right? If I do the slopes and things like that, then I can use that to get the velocity versus time graph, which is the second graph over here. And then you can see, right, velocity graph here, it starts, if you go from position A to zero, you are speeding up, but in a negative direction. So the graph here is you're speeding up, but in a negative direction, where when you get equilibrium position, which is right here, right? Let's say represented here, in terms of you get the highest speed. Then as you go, from from zero to x equals a, which is right here at this time, then you stop again, your velocity is zero. Then you speed up again to x equals, negative a. And in this case, you basically, you're going in a positive direction, right? So basically, this is from a to zero to negative a to zero to positive a and things like that. And again, zero, negative a, zero, positive a, and all of those things. So this is then velocity versus time graph, where you can see, right? So here you have a maximum velocity, maximum velocity, maximum velocity, and they correspond to basically position to be zero, right? So they correspond to position, as you can see, right? Position zero, x equals zero, you have then the maximum speed. But velocity zero corresponds to the maximum amplitude and things like that, right? So kind of like hard to do that graph. All right, so let me show you in a simulation where you guys can see some of this in a nice simulation. All right, so here, we have a lot of stuff over here, but let's start from this. So basically, we have a spring system. You can see right at the bottom, and the spring, system is then pulled toward the maximum displacement to the right, so it's equals to A. And remember, one of the things we have here is the force acting, after we let go of the system. So let's say if you take it, you pull it to the right and you let go. After that, the force acting on the system is the spring force, which is acting toward the equilibrium. So let's say when you're at the position x equals a, it is acting toward the equilibrium, which is to the left. And this equation is, F spring is equals to negative k times x. So this is this equation, which is known as a Hooke's law. Remember, so this is the Hooke's law equation, which tells you that for an elastic system like this, force is not constant, it's a variable force. The spring force is directly proportional to the x. So that's why more we stretch the spring or compress the spring, right, stronger the force magnitude. So it's not a constant force. But one of the things we have also, it's proportional to the negative of the x. And this is one of the reasons that, let's say, the system here is known to be simple harmonic, or when it undergoes a motion, it is a simple harmonic motion. Again, what is a simple harmonic motion? Simple harmonic motion is motion where the force that acting on the system every time it is displaced from equilibrium is going to be in the opposite direction of the displacement. So for example, see in the when you take the system and you displace it to the right, which is my x, from equilibrium, right? Force then will be acting in an opposite direction, which is to the left. But if you take this and displace the position to the left, then the force will be acting in the opposite direction toward the equilibrium, which is to the right. That means there is this negative sign that always present in this equation, indicating that force is proportional to the negative of the displacement. Or you can, if I take the force and replace it with mass times acceleration, and then is equals to negative, let's say negative kx. And then if I do acceleration equals negative k over mx, right? So that where the k over m is actually proportionality constant. Again, you can see acceleration is proportional to the negative x. So those are the two ways we can see that how the force proportional to the negative of x and how the acceleration is proportional to the negative of x. And in a way, then what we have is this is the reason that this motion is a simple harmonic motion. Because one of the things I can say here is this. Remember, acceleration I can write as d square x dt square. So d square x dt square then equals to negative of x. Okay, so let's ignore for the constant for a second. So that means one of the things we can do here is this. If you take x to be, some kind of function, right, whatever, right? So, and then you take that and take the derivative of that, or let's say f of t, right? And take it and take the derivative of that twice, then you get exactly the same thing as you started with, just a negative of that. Okay, that means this type of motion represents that. That means you start, the x is some kind of function, and then you take the derivative of that twice, because that's what we have, right? Acceleration. Take the derivative of that twice, and you end up with the same thing as you started, but the negative of that. And if this is true, then your system here is simple harmonic motion. That means it undergoes a simple harmonic motion. Okay, I'm going to show you that in terms of why is that, the case, right, for this type of motion. And I will show you, like, let's say when you look at this position versus time graph. So actually this one is, shows several graphs. So, but let's do this. Let's remove the energy graph for now because we don't really need that. And what I'm going to do here is this. So I'm going to start the simulation. So then the spring that is now is being stretched to position x equals plus a. And in this case, we're going to take this x equals plus a to be 5 meters, right? And let's say the black here is 5 kilogram, and then the spring constant is 100 newtons per meters. The idea here is to see that when we are at position x equals a, then this is the maximum displacement, which in a way means that this force right now is the maximum force, right? Because, since the force depends on the position and this is the maximum position, well, this is then maximum negative force. And if since this force is equals to mass times acceleration, so whatever we have about the force, same thing with acceleration. That means acceleration also has, direction as to the left, right? It's also negative because force is negative, and it's also the maximum, let's say, but it's negative just like the force. Okay, that means acceleration is maximum and negative, force is maximum and negative, and velocity is 0. Those are at x equals plus a position, right? So when x equals plus a, system has no velocity, doesn't have any velocity because it's going to start from rest. Acceleration is maximum and negative, force is maximum and negative, and then once we let go, it's going to undergo simple harmonic motion, which is oscillatory motion, right? And it's going to be called also simple harmonic motion because we're going to get a sinusoidal graph. And what we're going to see here is that if we take the x to be some kind of function, as a, f as a function of t, right? And if we take the derivative of that twice, we're going to get the same thing, but negative of that. All right, so let's go ahead and run this. And then you can also see the position versus time graph. Actually, there are like several graphs. There's also going to be velocity versus time and acceleration versus time, and even kinetic and potential energies, which we'll also talk about. So this I kind of like gives you all of those graphs. But let's see. Let me kind of clean this a little bit. So let me kind of clean those few things. All right. So now, what we have here is this. Let's assume that we take this, black, stretch it to x equals a, and then we're going to run. All right. And let's do kind of like a slow like this. All right. So let me reset this. Okay. I can't seem to reset. Oh, there you go. Okay. There you go. So let's look at the, slowly like this. So it goes between x equals plus a and minus a. All right, so let's do this. Let me make the black a little bit smaller so it's not like on our way. Okay, so think like this. So we're going to start over again. At x equals plus a, my velocity is 0. My acceleration is maximum, but negative. My force is maximum, but negative. And what we're going to do here is then we're going to look at in terms of, let's make it a little bit simpler. So what we're going to have here is this. As soon as I run, you're going to see how position versus time graph represents the motion. Remember, going from x equals a to x equals 0, it's going to speed up, going to the left. Then from x equals 0 to x equals negative a, it's going to then slow down, going to the left. Then it's going to stop, and then speed up to the right, and then slow down to the right. So that's going to be based in terms of position and velocity and acceleration graphs. So you can look at the velocity, in terms of what's happening with the system, oscillates between x equals plus a and minus a. And then you can see that, right? So for my, a position versus time graph, as soon as it reaches a, it starts from the top, right? And then it goes down and goes up and goes down. So basically it's a nice sinusoidal graph. It's basically a cosine function, positive cosine function. At the same time, velocity then is a, you can see, right, is a negative sine function. Acceleration is a negative cosine function. Even potential and kinetic energies change as a function of time. But this is what we have. That means if I want to look at how this graph can be modeled as a, for the x as a function of t, then I'm going to have to say that this is nothing but a sinusoidal function. It has to be a sinusoidal function. Now the question is that sinusoidal function, will then this function satisfy this particular statement? That if I take the, let's say my function, take the derivative of that twice, I'm going to get the negative of that. So we can see it from here. That means if I take x to be some kind of, cosine function, let's say cosine of t, for example, right? I'm going to simplify here. So let's say it's cosine of t. Then if I take the derivative of that once, so dx dt, so I take then the derivative of the cosine as a function of time. Well, the derivative of the cosine is then negative sine. Hopefully you guys remember that. So it's negative sine. Then I'm going to take the derivative of the second time. That means the derivative of the sine, negative sine t. Well, if I do that, then I'm going to get the derivative of the sine is just cosine, but there was also negative, so it becomes negative cosine t. Well, I got what I wanted, right? I started with x equals cosine. I took the derivative twice, and I got the same cosine, but the negative of that, which means this is a sinusoidal function. That means I can model this motion as some kind of cosine function. And that's what we're going to do. So we're going to go back to our slides and see how we can just model this in terms of the cosine function. And what are the important parameters, like over here, right? Remember, this was a proportionality constant that we have to include into our, equation. All right. So coming back here, then as I mentioned, right? So our graph is basically sinusoidal. So then if I'm doing position versus time graph, then if I stretch the spring, so let's say if I take that and then stretch it to position x equals plus a, and with respect to equilibrium, and then if I let go from here at t equals 0, then my graph starting from here going to change as a cosine function, right? So it's going to change as a cosine function, which is basically what I'm going to then use it to model it. So then x as a function of time equals, I started with the amplitude a, and it's equals to then a times cosine omega t. All right, so omega in this case is defined as the angular frequency, is the angular frequency of your system, and is defined as 2 pi over the period, or 2 pi times linear frequency. That means omega, angular frequency, is related to both linear frequency and then the period. So it's equal to 2 pi f, or 2 pi over the period. And it is one of the important constants in the simple harmonic motion, because that's the constant technically we put it here, but we can still write this as a cosine, for example, 2 pi f times t, or I can still write this a cosine 2 pi over the period times t. Any of those versions are technically correct. So it is a cosine is a sinusoidal function, and it is exactly what type of motion I get when the spring goes back and forth between maximum and minimum displacements, or positive and negative displacements. Okay, so this is a x x a x as a function of time equals a cosine omega t. Now I should also point out that technically the complete equation will be a cosine omega t then plus phase constant. So we're going to talk about this phase constant. So this phase constant is generally represent if you started your timer, at some position other than, let's say, x equals a. For example, imagine I take this, the spring system, and I stretch it to x equals a. Then I let go, but do not start my timer. So I wait until, let's say, it gets to, let's say, x equals 0, and on its way to the left, right? Then I start my timer. That means at t equals 0, my position x at t equals 0 is equals to 0 rather than a, let's say. That means if this is the case, that means I start my timer at later time when I let go of the system from from x equals plus a position, but start the timer a little bit later. Then this phase constant represents that information. Where did I start my timer? Because if phi here is equals to 0, we're going to talk about that. Then that means x as a function of time where t equals 0, I started at position A. That's why if I start at case, right, if object is released from rest at t equals 0, I should point like at x equals a, then we can model it in terms of this a cosine omega t plus, because the phase constant is 0. But again, if I wait until it reaches this position, then start, let's say this is my now, the graph, right? That means this is my t equals 0 graph. Then I basically have this pi over 2, right? This pi over 2 factor, and we're going to have to include that, but we will see a few examples where we can do that. All right. X equals a cosine omega t. So we can kind of simplify for now, assuming that we always start from a. The graph is, and the equation is x equals a cosine omega t. To find the velocity, well, velocity is dx dt. So I take that and take the derivative of that. So which is basically a then d dt of cosine omega t. So the derivative of the cosine is sine, or sorry, negative sine. But then we also have to do the derivative of the argument. So the derivative of the omega t is omega. So then we introduce omega there as well. So then velocity is equals to negative a omega sine omega t. Okay, again, negative basically because the derivative of the cosine is a negative sign, and a is because the amplitude was a constant. We remove that, and omega comes from the derivative of the argument of the cosine function. Now, in this equation, if I look at this equation for x, the coefficient in front of the cosine function is then my maximum displacement, which is a. And in this equation for the velocity, the coefficient in front of the sine function is also my maximum, but for the velocity. So the maximum speed then is a times omega. So a omega is equation for the maximum speed. So that means what is the speed at this point, or at that point, or at this point. And I can use this, right, position versus time graph, to use to graph the velocity versus time graph by always looking at this, so like a slope and things like that. All right. So, but since remember omega is equals to 2 pi f or 2 pi over period, I can also rewrite this in several ways, right? So replacing omega with 2 pi over period or 2 pi times f. So I have that. Additionally, omega related to the other two variables that we have in the system, which is the mass of the block and the spring constant K. And that is using this equation. Okay. Again, this comes from this. Remember that the force, spring force equals to negative kx, and then this is then I said mass time acceleration, which is the force, equals negative kx, and then the acceleration equals negative k over m times x, and then what we say is that this k over m is nothing but omega square. So omega squared times omega squared times x. That means omega squared is k over m. Or if I take the square root of both sides, then omega is equals to square root of k over m. That means omega, that's why omega is kind of like important variable, because it relates all of those variables. So these are my equations of motion. So this is equation 1 of motion, which is position. This is equation 2 of motion, which is the velocity. And we're going to see there's also equation for the acceleration, which I can do here, right? Acceleration as a function of time is equals to, well, taking the root of this equation 2. Let's call this equation 3, right? So that's basically going to be negative a omega, then take the derivative of sine, which gives me cosine of omega t, then take the derivative of the omega t, which is the argument of the cosine, and that gives me another omega, so I square that. That means this is then the equation for the acceleration as a function of time. So I have 1, 2, 3, those three equations are equations of motion. Then these equations are basically equations of the system variables. So we have angular frequency, linear frequency, spring constant K, mass of the block. That means those are the sort of like, let's say, my variables. So again, angular frequency, linear frequency, period, mass of the block, and spring constant K. And in a way, those equations relate all of those things together. Okay, so that's why omega is kind of like the link between all of those things. Because omega is equal to square root of K over M, but omega also equals to 2 pi F, I can use that to relate Km to linear frequency. And because omega also equals to 2 pi over the period, I can use that to relate M and K to the period. And that's the equation. So this equation is sometimes useful to remember because that's the period of oscillation. And you can see where the period of oscillation, that means, how long does it take for the system to go back and forth one time? You can see, right, it depends only on the mass of the block. That means if I take the system and pull it 5 centimeters or 10 centimeters or 15 centimeters, period is unaffected by that. That means you're going to get exactly the same period back and forth. Even if you, like, let's say, stretch it double the distance, something like that. The only thing will affect this, the period is if I change the mass of the block. And obviously, let's say the spring constant K. That means I'm using different spring constant. Then the period and frequency will be different. All right, so let's look at a simple example over here. It says determine the period and frequency of a car whose mass is 1400 kilogram and whose shock absorbers have a spring constant of 6.5 times 10 to the 4 newtons per meter after hitting a bump. Assume the shock absorbers are poor, so the car really oscillates up and down. All right, so we are given the mass, which is 1400 kilogram. We're given the spring constant K, which is 6.5 times 10 to the 4 newtons per meters. And I want to find period and frequency. All right, so one thing I know here is period and frequency, if you remember, right? Let's say if you don't remember, try to remember this equation. Omega is equals to square root of K over M. And then omega is equals to also 2 pi times F. And omega is also equal to 2 pi over the period. That's why you can say, right, omega kind of relates all of those. So since omega is equal to square root of K over M and 2 pi F, then you can say 2 pi F is equals to square root of K over M. Or F is equals to 1 over 2 pi square root of K over M. And then you can just plug in and calculate, right? So 1 over 2 pi square root of then 6.5 times 10 to the 4 divided by 1400 kilogram. Then you can calculate the linear frequency from here, and we can calculate this to be 1.09 hertz. For example, that's one thing we can do. And then I can remember that angular frequency, since it's equals to square root of K over M, and it's also equals to 2 pi over the period. So I can rearrange this and get that the period is equals to 2 pi square root of M over K. I can use this equation, or since I have the frequency, I can say then, you know what, period is 1 over the frequency. So then I can use this to calculate this to be 0.92 seconds. So those are basically our answer for this. Right, so here's another example. The cone of a loudspeaker oscillates in simple harmonic motion at the frequency of 262 hertz, which is middle C. The amplitude at the center of the cone is given as A equals 1.5 times 10 to the negative 4 meters, and at T equals 0, X equals A. Now, what equation describes the motion of the center of the cone? So then we need to find out in terms of how to write down that equation for position. Then what are the velocity and acceleration as a function of time? And what is the position of the cone at t equals 1 millisecond? That's basically what we need to do. All right, so for part A, we have then x as a function of time is equals to a cosine omega t plus phi. Okay, now let me show you then why phi equals 0 when x equals a. So we are told that at x when t is equals to 0, position of x is a, right? So that's a given, information. We also know that x as a function of time is equals to a cosine omega t plus phi, but t is 0 because we are taking this time where t equals 0. So if I plug in over here, then on the right side of the equation, this is equal to an a cosine of omega times 0, 0. So it becomes a cosine of phi. Okay, that means this is the right side of the equation. This is the left side of the equation, which is here. That means x is equals to a. The right side of the equation, and a cosine omega t plus phi becomes a cosine phi because this term goes to 0 since t equals 0. That means we end up with a is equals to a cosine of phi. Well, I can cancel the a, which then gives me 1 is equals to cosine of phi. And phi then, when you do inverse cosine of 1, gives you 0. That's why then I can say that phi is 0. So then I should not be including that in my equation, or I can just say right away that phi is equals to 0. Next, then x as a function of time is equals to a cosine omega t. That means I can ignore the phi because it's 0. My question is, what is a? Well, a is given as 1.5, or let me write down here. This is as 1.5 times 10 to the negative 4 meters. That's for a. Then cosine, and then I'm given omega plus omega t. Well, omega t, I don't have omega directly, but I have the linear frequency in hertz. So I can just write down this is just 2 pi f, which is what omega is, right, times t, and then just calculate what the 2 pi f is. And that's basically, let me do it here, right? So omega is equals to 2 pi times 262. So that should give me, in terms of 1,650 radians per second. Okay. Then I can come back and say it's 1.5 times 10 to the negative 4, then cosine 1650t. So that's my a as a function of time. Part B, then just taking the derivative of that, right? So then Vx is equals to then dx dt. And remember, it was equal to then negative 8 omega, then sine omega t plus phi. So then phi equals 0. Then I can say this negative 1.5 times 10 to the negative 4 times 1650, then times sine of 1650t, which gives me, if I multiply those two, remember those two together is actually Vmax. So if I do that, I'm going to get 0.25, so negative 0.25 meter per second, then sine 1650t. Okay. Same way I can do for acceleration as a function of time, which remember end up being negative omega squared times a cosine of omega t. So then this is equals to negative, again, omega square, omega is 1650, square that times amplitude, right? Will end up giving me 408.4 meter per second square, which is then nothing but a max, right? Maximum acceleration, then times cosine of 1650t. That's my then velocity and acceleration as a function of time. Last part says, what is the position of the cone when time is 1 millisecond? So I go to this equation for the position, and I use that to find, for part C, right? Okay, so what is the position when t is equals to 1 millisecond, which is basically 10 to the negative 3 seconds. So then 1.5 times 10 to the negative 4, then cosine 1650, then times 10 to the negative 3 seconds. and I calculate, and I'm going to get negative 1.2 times 10 to the negative 5 meters. That means it's 1.2 times 10 to the negative 5 meters to the left of the equilibrium position. All right, so another thing we can have is when we are looking at this, the spring system going back and forth, if we kind of look at the shadow, so this is kind of like if you're looking at the shadow of an object kind of going around in a circle, and this is kind of very similar. So you can see, right, a figure of a shadow movie of a ball made by projecting a light past the ball and into the screen. So let's say you have a turntable, the ball going back and forth. So its motion kind of goes back and forth. If I take this to be like, let's say plus A, this part negative A, and this is equilibrium, then you can see, right, the ball goes back and forth between that. So that means the ball moves in a uniform circular motion, but the shadow moves in a simple harmonic motion. So the black on a spring in figure, right, moves with the same motion. So sometimes we can, let's say, make analogy, right, of the particle moving around in a circle and then going back and forth. Its motion can be modeled as a simple harmonic motion. So for example, this is here as, let's say, similar to when the spring here is at A, then this is the ball going to x equals 0, then to x equals negative A, then come back to x equals 0, come back to x equals A, and then repeating the cycle back and forth, back and forth. So its shadow basically represents that type of motion. Again, here's a nice simulation which shows the particle going around in a circle. So it's a circular motion. But you can see that this is, if I'm looking at the shadow of that, it's pretty much behaves like a simple harmonic motion. If you look at it from the side view, right? Basically it goes back and forth between, plus A and minus A. So speeding up, then starts slowing down, then stops, then speeding up, moving fastest at the center, slowing down, stops, and back and forth like that. So this is basically, pretty much, in terms of this object going back and forth like that, you can see, you can model it as a simple harmonic motion. And it becomes sometimes useful specifically if you want to find that phase constant, because it can help you to figure out when and where you can have the phase constant that is non-zero, and how to find that sometimes is useful using this circular motion, let's say, analogy. All right, so let's go back here. So then here's one thing we can do. So let's say, what if an object in simple harmonic motion is not initially at rest at x equals 0, when t equals 0? Then you can say, right, then we may have to use the cosine function, but with the phase constant. So that's right here. See, the phase constant now included. So this phase constant is in units of radians, right? And it again represents a shift, right, of the graph, let's say, when the object doesn't start from x equals a at t equals 0. So you can write in this case, what we have here is equation 1, equation 2, and even equation 3, right, for the acceleration. Then includes this phase constant, phi naught. So then in a way you can think like this, right? So this phi naught here is sort of like an angle. See, if the particle starts from here, so then, this line is right here, and then obviously that's a phi equals 0. If the particle, let's say, is kind of, stretched to x equals a, this is equilibrium. So think like this. If you let go from here, but then start the timer somewhere over here, so you can see, right, then it moved this angle phi naught, right? So this move this angle phi naught over here, and then you can then, let's say it's somewhere over here, and then you start the timer at t equals 0. Then you have to kind of find that angle phi naught. And then we can use this then, let's say, a circular motion as an analogy, to try to get that, let's say the constant, phase constant. Okay. So here's an example. So let's say oscillation described by the phase constant, where phi naught is equals to pi over 3 radians, or negative 3 pi over 3 radians, or pi radians. That means you have 3 different scenarios: pi over 3, 3 pi over 3, and pi radians. And you can see, right, so it is easier to see from here, right, using the circular motion, that pi over 3 or 3 pi over 3 basically depend in which direction is the particle moving when we start the timer. For example, if I take this to be the, let's say, my initial starting point, right, when I start the timer, this is, remember, this is A, this is 0, this is negative A. So this is the time, or the instant where the object is moving to the left, right, is moving to the left, and is between A and 0, but it moved basically pi over 3 radian equivalent distance, but it is moving to the left toward the equilibrium position. And this particular graph, if I apply it here, see, let's say this would have been my A starting from here, but now there's, a shift like that, right? So there's a shift like this, pi over 3 shift. So let's say instead of this, right, there's a pi over 3 shift where this is my, t equals 0 line right now. That means now when I do x comma t, then this will be a cosine omega t plus then pi over 3. Okay, again, why plus pi over 3? Because the particle, right, so if you take clockwise this from the, let's say x equals, 0 line, right, or phi equals 0 line, it is clockwise, so it is pi over 3. So phi naught here is pi over 3. And you can see in terms of it's also in which direction it is moving, right? It's moving to the left. Then the phase constant, that means, you are pi over 3 radians, shifted from to the right, from x equals, a. Right? So this is a positive pi over 3. Basically, you shifted your graph to the right of that. Then this is the same phase constant, pi over 3, but you can see, right, this is the portion where the particle is moving to the right. That means it started from here, it went to the negative a, then come back to 0, and then it goes from 0 to positive a. And this is during that motion, basically from equilibrium to going to the negative a. Which means that if this was my graph, right, so this, remember, cosine graph, now I am pi over 3 behind that, which means that negative pi over 3 behind it. That means I am behind pi over 3 radian from my actual x equals a graph. That means then my phase constant is negative pi over 3, because again, right, if I do this graph, which is clockwise from my reference line, then that phi is the negative pi over 3. So that means, this, so this, think of like this. This is for the A, this is for the B. So I can say x comma t is equals to a cosine omega t minus pi over 3. Okay. All right. So then if I'm looking at this, the object started from here, but I didn't start the timer until it reached the negative a, and then I started the timer. That means, I am, you can see, right? So if this was, let's say, my graph like that, so I am, exactly pi, to the right of that. So that means, it's equivalent to me shifting the, the T0 line, exactly pi radians to the right. Okay. Then this will be x comma t is equals to a cosine omega t plus pi. So that's basically will be for that. So that's why you have then phase constant representing more or less where exactly your graph has, started, right? So let's say, when did you start your timer? Where the object moved with respect to this, x equals plus a. Is it, on its way to the left or on its way to the right? And those then determine in which direction. Generally, when it's moving to the left, the phase constant is positive. When it's moving to the right, the phase constant is negative. All right, so let's look at an example here. Suppose the spring in example 4, where omega is equals to 8.08. Well, actually, I didn't do that example yet. We will do it later on. But let's say you have a spring that has an angular frequency of 8.08 radians per second. That means, let's say omega is equals to 8.08 radians per second, is compressed 0.1 meter from the equilibrium. Okay, so let's say you have a spring that is, this is the equilibrium position. It is compressed and sitting here at x equals negative 0.1 meters. But it's given a shaft to create a velocity in a positive x direction of v naught equals 0.4 meter per second. Okay, so Those are kind of like our initial conditions, right? So we're given V naught is equals to zero point 0.4 meters per second. All right, so we're going to determine the phase angle phi. So this is basically just phi naught, right? Same thing. The amplitude, the displacement x is a function of time. So we're going to have to do all those things for this, assuming that we are given that angular frequency is 8.08 radians per second. So that's one information that, let's say, we're given. So our goal will be to get the phase constant. And to do the phase constant, we have to involve, two equations. So equation one, let's say, will be for the position. So let's say x when t equals 0, let's call this x naught. So this is then a cosine omega t plus phi, right? Remember. But since this is basically my, this x naught is just x when t equals 0, okay? So this term goes to 0, right? Because if I plug in 0 for t, that it goes to 0. So technically this equation 1, x naught equals an a cosine of phi, or phi naught, same thing. Then equation 2, which is for the velocity, where velocity is equals to negative omega a sine of phi naught, which is again same idea that omega t here inside the argument of the sine is 0. So you have then equation 1 and 2. Okay. Now, one of the things that we can do here, if I rewrite this equation 1 over here, which is a cosine phi naught. All right, so equation 2, equation 1, and what I do here is I divide 2 over 1. That means, I'm dividing this like that. So on the left side, I have then V naught over X naught. And on the right side, A's cancel out. Then I have negative omega, and then sine of phi over cosine phi, which gives me tangent of phi naught. That means what I end up with this tangent of phi naught is equals to negative V naught over omega X naught. And you can see, right, from here, I can already calculate what my tangent of phi here is. Let's do it over here because we have more room over here. Okay. So tangent of phi naught is equals to negative 0.4 meter per second over 8.08 radians per second, then times negative 0.1 meters. Right. So calculate that, I'm going to get 0.495. Calculating all that, get 0.495. That means tangent of phi naught equals 0.495. Then calculating phi naught gives me 3.6 radians. That means that's my then phase constant phi. Okay. This was part A. Part B, it says find the amplitude. All right, so I am not given amplitude directly because this x naught is not the amplitude, remember, right? So then amplitude I can get from this equation, basically of the position, because now I have x naught is equals to a cosine phi, or phi naught. Now that I calculated cosine phi naught, remember, in this portion here, I eliminated amplitude even though I didn't have it, right? I eliminated it, so that's why I didn't really need to know that. But now here I can use either velocity equation or the position equation to find the amplitude, and it's easier to use the position equation. That means, amplitude is equals to x naught over cosine of phi naught, which means that amplitude is equals to negative 0.1 meters over then cosine of 3.6 radians. And remember one thing, that when you're doing this type of calculation, make sure your calculator is set to radians. If we calculate, we can get 0.112 meters. That's my amplitude. All right, so basically 11.2 centimeters. Part C then says, find the displacement as a function of time. That means write it down. So then I can do this. X as a function of time is equals to its amplitude, 0.112 meters, then times cosine of omega, which is 8.08 times t, then plus 3.6 radians, and that's the phase constant. That means this is basically me writing this general equation, right? So x as a function of time is equals to a cosine omega t plus phi naught. And that's the equation for, x as a function of time. That's for part C.